In this section, we learn how to factor polynomials of degree 2 using shortcuts. And we're going to start with the difference of squares. So this section 6.5 is actually related to the previous section we've seen in chapter 5 on special products, and it's found in 5.6. So if you look at 5.6, we've seen in that section, for instance, that if we multiply a plus b times a minus b, we are going to get a difference of squares. So of course we could always like multiply it term by term like this, okay? But in what's going to happen is that as you multiply a with minus b, you're going to get minus ab, and as you multiply b with a, you're going to get a plus ab, so they sort of cancel out. So that's why you're just left with the a times a and the b minus the b times b. So you're left with a squared minus b squared. So this is an identity that's quite practical because you can save time if you have to multiply polynomials together. For example, if you have to multiply this, well, you recognize this is like an a minus b times an a plus b, so you're going to get a difference of squares. You're going to get a squared, x squared minus 3 squared, so minus 9, and we immediately get what the product is without having to simplify. Now, in this section, we're going to go backwards. That's the idea of factoring. We're given, for instance, something like this, and we want to express it as a product, so we just have to read this equality the other way around, and we see that immediately we can factor it as a plus b times a minus b. So let's take a look at some examples to see how this works. So first example, I've got x squared minus 16. So I'm in a situation that's very similar to this, right? The only difference is that I don't have a 9, but a 16. And we can recognize, okay, so this is something you might want to do in your head, but I'm going to write it down so that you can see what's going on. I'm seeing the 16 as something squared. It's 4 squared. So what I have here is a difference of squares. So I'm going to write it as x minus 4 times x plus 4. Now the order doesn't matter. You can also write it as x plus 4 times x minus 4. It really doesn't matter how you write it down. So okay, so this is reading this identity backwards. I could have something like, oh, by the way, well, maybe let's look at something like of the form x squared minus 7. Now you might think, oh, this is not a perfect square here. This is not something squared. Nothing squared will give me 7. Well, that's true if you work with integers, but it's not true if you work with real numbers. So in fact, any positive number is the square of something. It's the square of its square root. So I can always see the 7 as square root of 7 squared, right? So by seeing it this way, I can write that as a difference as x minus square root of 7 times x plus square root of 7. So once again, as a minus b times a plus b. So as long as you've got, let's say, something like x squared minus minus some number, you can always some positive number, I guess. You can always write it as think of it as a difference of squares and factor it. So let's take a look at another example. Minus 25b squared plus 9a squared. Now, is that a difference of squares? You may think, oh, there's a plus here, so it's not a difference. But let's be careful here. There's also a minus here. So in some way, if we reorder this, there is a difference of 2 terms. Okay, so I may think, oh, 2 terms, a difference. Maybe it's a difference of squares. So let's see if I can think about the first term as something squared. Well, 9 is 3 squared, and a squared is a times a. So if I squared 3a, I'm going to get back 9a squared. And same goes here. If I squared 5b, oh, I'm going to get 25b squared. So I do get a difference of squares. So that's going to be 3a plus 5b times 3a minus 5b. See, on purpose, I've decided to start with a plus sign here just to show you that it doesn't really matter. But what's important is that you have a plus and a minus. Okay, you can have two pluses, two plus signs and two minus signs. That's impossible. So example D, let's say I have x squared plus 36. Now that's not a difference of squares. I've got something squared plus another thing squared, right? The 36 is 6 squared. When you have that, it cannot be factored. So when you have a sum of squares, it cannot be factored. So this is something to remember. A sum of squares cannot be factored. Which means that if I add it here, a squared, if I have a squared plus b squared, it cannot be factored. So in the book they call that a prime. So this is to draw an analogy with numbers, and when you have a number like 7 and you want to write it as a product of integers, the only thing you can do is write it as 1 times 7, we say that number is prime, right? For example, 6 is not prime. You can write it as 2 times 3, but those two are prime numbers. So when an expression cannot be factored more into simpler polynomials, we're gonna say it's prime. At least the book will say it's prime. Now we move to a fifth example. 2x squared minus 7. Okay, so we see a term here minus another term, and we can try to think, well, is there something squared that's going to give me 2x squared? Well, try to think as 2x squared, as there's x times x, so that's good. We can there's probably an x here, something times x squared will probably give me 2x squared. Well, what's missing in front of my x? Well, think of your 2 as square root of 2 times square root of 2. So once again, this is square root of 2 times x squared. So I say once again, it's similar to this example here where I thought about 7 as square root of 7 squared. So remember that every time you've got a positive number, you can always think of it as the square of something. It's the square of its square root. Okay, so and minus 7, well, that's root of 7 times root of 7. So what I can write here is minus root of 7 squared. So I've got a difference of squares. So this is like a squared minus b squared. So it's going to give me a plus b times a minus b. Pay attention to the way you write your square roots. The square root here, it needs to end after the 2. So you don't want to write this, right? Because that's going to be square root of 2x. That's not what I want to write. I want to write square root of 2 times x. So if that bar does not extend further, it means that it only affects what's underneath it. Usually we tend to put a little, sometimes I tend to put a little dent here so that the reader can see that it ends after the 2. Okay. You may think, okay, well, actually, all these, well, actually, some of these here, actually, all of these are polynomials of degree 2. Right? So technically, why have this trick? So like maybe I could factor it using the techniques from the previous section 6.4, right? Because I can think of all these polynomials as being of the form ax squared plus bx plus c, or maybe with two pair variables, ax squared plus bxy plus cxy squared. and then just apply the techniques from the previous section. Well, let's see how that goes. I mean, you can always rely on that technique. It's going to work all the time, but I'm going to show you that without the shortcuts we've used here, it's going to be a bit more difficult. So some examples revisited. So I'm going to revisit example, which one? Example 8, let's start with that. X squared minus 16. So I may think, oh, this looks like something like x squared plus bx plus c. Well, there's no x, right, in the expression, but there is if I just add a 0x, right? So I can always think of that polynomial as being x squared plus 0x minus 16. And according to the technique from this is what section 6.3, my a is 1, right? A is 1, the coefficient of x squared is 1, b is 0, and c is minus 16. So I'm looking for I'm trying to find two numbers such that the product is c and the sum is 0. So I can look at the factors of 16 and like that, and 4 and 4. And if the product is minus 16, means one's positive, one's negative. Okay, so that means their difference must be equal to to 0. So 16 and 1, their difference is not 0, obviously. 2 and 8, their difference is not 0. 4 and 4, okay, yeah, the difference is 0. So the two numbers are looking for are 4 and minus 4. Okay. So that means it's x, well, remember, x plus the first number times x plus the second number, and indeed I get x plus 4, x minus 4. But that was more work. Like if you don't know the shortcut, that's definitely more work, because I have to think, okay, actually there's this 0x here that I need to include, and then I need to find the two numbers. See, and then, okay, after that, I've got my factorization, but it was definitely more work. It wasn't too bad, though. Well, let's look at, it gets worse if I look at more complex examples. I'm going to revisit, this is B, no, this is C I'm going to look at. C. So we've got what? We've got minus 25b squared plus 9a squared. Okay. So that's a polynomial with two variables. So once again, I need to introduce the middle term. What's the middle term? It's a term that has a times b multiplied. So its coefficient is going to be 0. Okay, so now that's like my coefficient, my first coefficient, right, which I call A. I'm going to put capital A so that you don't get confused with the lowercase a, which is used as a variable here. So the first coefficient is minus 25. My B, the second coefficient, is 0. And the coefficient of A squared, that's my C here. So what do I need to find here? To factor this, I need to expand the middle term, and I need to find two numbers whose product is what? It's going to be A times C. So what's A times C? It's 9 times 25, so that's minus 225. Already, you have to do a big multiplication, and I know some of you are not too fond of this. So, and the sum is B, right? Sum 0. So then I need to, and then you need to know pretty well the factors of 225, and that's a big number to work with. I know, because I kind of know my multiplication table pretty well. Okay, that 225 is a perfect square, so 15 times minus 15 will give me 225, and they will add up to 0. So if I know this, I'm okay with that technique, but already it's taking me more time, and I have to deal with large numbers, so I'd have to split my middle term using those two numbers. So here I'm using the technique, the AC method, right? It's the technique from section 6.4 now. It's not the same as in the previous example because my coefficient, I didn't have a coefficient of 1 for either a squared or b squared. So I'm kind of forced to use factorization by grouping. Okay, I split my middle term, then I group them, and I factor by grouping. I recognize I've got 25 and 15. Those are two multiples of 5. I've got a b that I can take out, so I get 5b minus 3a. And over here, I've got 15 and 9 are two multiples of 3. And I can take out an a, so I got 5. I wrote AC, but this is a B here. 5B plus 3A. Now, take a look at this. The teacher did something bad, or okay, they should be the same. If I picked my numbers correctly here, those two numbers, after factorization by grouping, I should have a common factor. So something's wrong. I didn't get the same factors here. So either my numbers are wrong, but if I look closely, they're not. Either my factorization by grouping is wrong, and it is. There's a mistake that I made. Because I'm taking out here 5 minus 5b, this needs to be a plus, right? So that when I multiply minus 5b by 3a, I do get back the minus 15ab. So I made a small mistake. So I do have the same factor, and then I can take away that common factor of 5b plus 3a, and then I'm left with minus 5b plus 3a, and just notice that the minus 5b plus 3a, I could write it as, well, I could actually reorder everything here. I'm going to write the 5b plus 3a as 3a plus 5b, and minus 5b plus 3a as 3a minus 5b, and we're done. I got the exact same thing I had before, which was this. Right? I hope you'll agree that that was more effort. Okay, so if you fall back on the AC method all the time, it's going to take you much more time, and maybe you're going to have to deal with larger numbers. So, okay, we can write oof. That's not something I'd like to repeat. Okay, so it's a lot easier to see this and see, oh, that's probably I have two terms. There's one's positive, one's negative. Oh, maybe that's a difference of squares. Okay. So it's a lot easier to factor this, and maybe I'll finish with example D that I'll revisit. X squared plus 36. Okay, so remember this is a sum of squares, right? So I told you this cannot be factored. Let's see how we can actually see this by trying to apply the AC method. So trying to apply the AC method, I would introduce a 0x in the middle, and I've got A, which is 1, B, which is 0, and C, which is 36. So I'd be looking for two numbers with a product of 36 and a sum of 0. So if the sum is 0, it means one's positive, one's negative. But on the other hand, if one's positive and one's negative, the product is not going to be something that's positive, right? So if I've got a product that's positive, I cannot have two numbers that will add up to 0, because that would mean one's positive, one's negative, in which case I'd have a negative product. So that shows you that this is really impossible. Okay, we cannot find those two numbers, and therefore this polynomial cannot be factored. So there are no solutions here for this this little problem. So this means that this polynomial is prime. Okay, so I'm done revisiting the examples. Okay, so clearly I hope I've convinced you that you don't want to. This is not something, okay, you want to do. Okay, so don't do this. Don't do this unless you are really stuck. Really stuck means, oh, you don't remember what's the identity for factoring a difference of squares. Okay. What you really want to do on an exam is this. You want to be able to do this, okay? Because this is way more efficient. Okay. So I'll just finish with further examples. So we still want to factor. This time I've got a to the 4 minus b to the 4. So you may think, oh, that's not a squared minus b squared. Okay, so there's nothing I can do here. But hang on. A to the 4, you can actually think of it as it's a squared squared, right? Because when you squared a squared, right, you got a squared times a squared, and you got 4 copies of a. So that works. And b to the 4, that's b squared squared. So you do have a difference of squares. It's just that this is kind of like a squared times b squared, where a is little a squared. So that's going to give me, okay, let's do it slowly here. I'm going to get a plus b times a minus b, but big A is actually little a squared. So that's little a squared plus little b squared times a squared minus little b squared. Okay, so of course, this part is, well, this part I did here, that's something that you usually do in your head, okay? Just saying, oh, that's what's inside the bracket, that's like something squared, so it's going to show up here and here, and the b square shows up here and here. And after that, we may say, okay, we're done, but we're not. This part's prime, right? So we cannot factor this some more because it's a sum of squares, but this is, again, a difference of squares. Oh, so we can keep going. So this, I cannot do anything with it, but the other part, oh, that's a difference of squares. And now I'm done. That would be my final answer here. And last example, if I have 9, let me check, maybe I've done actually an example like that before. Yes, I did. So actually we're done. That's all I wanted to show you. That was a video that was a bit longer than usual, but I thought it'd be better just to have it as a single video with all the examples on difference of squares. Okay.